And the question I want to start with is, does the use of ultrafast weapons change the dynamics of animal fights? So by dynamics here, I mean both the behaviors that animals use during fights, and then who wins fights, or what are the characteristics of winners and losers of fights. So let's start with just a brief foray into animal weapons. By animal weapons, I mean in large structures that animals use, usually during intraspecific aggressive interactions. So these are things like the enlarged claws of fiddler crabs and many different types of crustaceans, jaws and jaw muscles in many different types of lizards, and horns in everything from dung beetles to deer. Okay? So animal weapons are pretty widespread through both vertebrates and invertebrates, and we actually know a fair amount about how animals fight using these weapons, which I'm going to refer to as classic weapons for the purposes of this talk. So this is an example of a fight with classic weapons. This is from a Denon, Moser, and Christie paper in 2012. These are two fiddler crabs fighting. There's one individual here, you can see his enlarged claw, and the other one here with his claw. And I'm going to play this video and describe to you the dynamics of this fight, or just what's going on. So we can see they're shoving those claws into their faces, right? They're doing this aspect of claw display. They intertwine their claws and then slowly exert forces. One animal gets flipped, and that's the one that gives up, right? So what's interesting is these dynamics, the way these fights pan out, are pretty similar throughout these different types of classic weapons. We start with this aspect of behavior, so usually this display behavior, displaying the weapon, which then can often lead into the exertion of force. So in the fiddler crabs, we saw these animals intertwine their claws and then slowly exert that force over several seconds, right? Usually, the individual that has the weapon that exerts greater force is the one that wins the fight. And we see this in vertebrates and invertebrates, so crayfish and shore crabs, these are just a couple examples, and different types of lizards like collared lizards and adult lizards. What we also see in these weapons is sometimes individuals are able to avoid having to use force and instead can win just by displaying their weapons. Usually they display a larger weapon. This happens in a lot of different types of crustaceans like crayfish, fiddler crabs, and snapping shrimp. So these are the dynamics of classic weapon fights that we're talking about today. Aspects of display behavior and force. Usually individuals that exert greater force win, or individuals can win by displaying a larger weapon. So now I'm going to take us into ultrafast weapons, and we can begin to think about how these fights might differ. Our example of ultrafast weapons today are mantis shrimp, or stomatopods. And this is what a mantis shrimp looks like. You can see the eyes are here, the body extends, is curled around, the tail is curled in front of the face. Here's another individual, so these two individuals are fighting. Now what I'm going to circle and enlarge here is what's called the raptorial appendage, and this is the ultrafast weapon of mantis shrimp. So this appendage uses a system of muscles, springs, and latches to store elastic energy, and then release that energy and swing out at ultra-fast speeds and accelerations. And what we're talking about here is speeds of up to 30 meters per second, an acceleration of the same order of magnitude as a bullet leaving a gun. So these things are moving very, very fast. To get you an idea of what that looks like, this is a video of a mantis shrimp strike, a high-speed video filmed at 30,000 frames per second and played back at 30. You can see the eyes of the animal are here, the body extends outside of the field of view, and this is that raptorial appendage. You'll see it swing out and strike this snail. Let me do that again because it skipped a little bit. There you go. So these things are moving real fast, right? And what they're able to do by having such a high acceleration is exert a very high impact strike force for their body size. So this is what a typical force trace looks like for a mantis shrimp strike. Our force is here on the y-axis, time in milliseconds on the x. We can see there's zero force, and then when that appendage contacts, in this strike we get a force of about 85 newtons. And it's really important to note here that this animal's mass is only 2.5 grams. Right? So a lot of force for a very small animal. So what does it look like when these animals use their weapons during fights? This is a video we took of two mantis shrimp fighting in Panama. It's kind of hard to see. It gets a little bit better when it starts to play. But there's an animal here, and its tail is curled up in front of its face, just like we saw in that picture earlier. This is its little burrow that it's living in, right? Here's another animal here that's going to lunge inside that burrow. What I want you to do, if hopefully we can see it, is get an idea of the dynamics of this fight. Specifically try to see how these animals are using their weapons during the fight. Did everybody get that? No, right? So it's really hard to see, right? So I'm going to slow it down. This is the same video at half speed, And I'll try to play this one a couple times because the quality is a little bit rough. But again, try to see how they're using their weapons. It's still really difficult at half speed, right? Let me play it one more time. Hopefully you can see that animal inside the burrow. So you can see them lunging toward each other, but you can never actually see the weapons move out to strike, and that's because they're moving so quickly, right? So visually, when we compare this fight to what we saw in the fiddler crowds, what we see in classic weapons, we see visually these fights occurring in different ways. We see different dynamics. Well, what we were interested in doing is more quantitatively comparing the dynamics of these fights with classic weapon systems. So our question again is, do ultrafast weapons change fight dynamics? And specifically we asked here, do competitors use weapon displays, as we see in classic weapon systems? And do winners of fights have weapons that exert greater forces than losers? Okay? So to do this, we looked at 34 sex and size match fights of a mantis shrimp from Panama. Before the fight, we measured each individual's maximum strike force, so their highest peak force out of 10 strikes. We also measured each individual's body length and their body mass. Then during the fight, we looked at their initial fight behavior, so looking for weapon displays, and we also looked at the number of strikes they delivered during the fight. All right? So to our first question, do competitors use weapon displays? This is what a weapon display looks like in a mantis shrimp. You can see those weapons are kind of pulled out to the side and a little bit ventrally. And what I'm going to show you here is a table of the first behavior that they used during the fight, and then the proportion or percentage of fights that began with that behavior. So about 15% of fights began with tracking, just looking at the competitor, or maybe flicking their antennae in this kind of chemosensory behavior. 35% of fights began with one competitor giving that weapon display, and only 18% of fights began with both competitors exchanging that weapon display, like we see in a lot of the classic weapon fights. What is also interesting here is that one or both competitors escalated directly to striking, so no antenna flicking, no weapon display, just straight hitting each other in 32% of fights. And only one out of our 34 fights ended after the weapon display. So every other fight escalated to striking at some point. So what these data suggest is that weapon displays are used in mantis shrimp, but they're by no means the rule, and they definitely aren't often used to determine the winners and losers of fights. Winners don't usually win just by displaying their weapons. Okay. So let's move to the second question here. Do winners of fights have weapons that produce greater force? So for this, I'm going to show you a table of 4 variables that we measured. So our strike force here, body length, body mass, and the number of strikes delivered during the fight. And I'm going to show you the winner minus loser mean, and then a significance test of that mean. So if our hypothesis is that winners of fights have weapons that produce greater force, we predict a winner minus loser value that's significantly greater than 0. Right? What we actually see is that winners and losers don't differ in their strike force, and indeed, losers strike with just slightly but non-significantly greater strike force than winners. What we see with winners is that they have slightly or significantly longer bodies than losers. They have more massive bodies than losers, and winners strike a significantly greater number of times during a fight than losers. And if we compare these values using a measure of effect size, we can see the effect size is greatest for number of strikes, which suggests that the winner minus loser difference is greatest for this variable. Okay. So to depict this visually, we took these values and we used a z-score standardization just to put them all on the same scale, right? And this is that plot. Here's our winner minus loser z-score on the y-axis, and our 4 variables here on the x. You can see first that there's a lot of variation in strike force, right? This is really variable between winners and losers in fights. We can also see that there's a really intense positive skew in number of strikes, right? And this is reflective of the fact that this was a very consistent difference between fights. So in only 4 out of our 34 fights did a loser strike a greater number of times than the winner. Right? So let's take these data and bring them back into our initial question of, do ultrafast weapons change fight dynamics? If you remember when we talked about classic weapons, we had this display behavior that usually started the fight, which then escalated to the grasping of weapons and the exchange of force, usually over several seconds. Usually individuals could win by having weapons that exerted greater force, or they could avoid force and win by just displaying a larger weapon size. Okay. What we see in our ultrafast weapons is we don't see this connection between force and winning, right? Because winners and losers don't differ significantly in their strike force. We also don't see this direct connection between behavior and winning, right? Because we don't see many fights end just after that weapon display. Instead, what I think might be going on in this number of strikes variable is this really cool interaction between behavior and force, in that individuals can behaviorally strike a greater or lesser number of times, and the individuals that strike a greater number of times during a fight are the ones that win the fights. Now, I don't mean to say that display behavior and striking behavior are the same thing. Those are obviously very different types of behavior. But what I was hoping to do in this talk, and what I'm thinking about for my dissertation a little more broadly, is how we can use similar terms and how we can compare different types of weapons, and especially use the interesting, cool, ultra-fast weapons of mantis shrimp to enhance our understanding of how animals use weapons to win fights, and to think a little bit more broadly about weapon evolution in general. Okay. So I'd be really, really interested in getting people's feedback on this framework idea, on this comparison between classic and ultra-fast weapons, and on any ideas for future work that we could look at in this system. Before I end, I just want to really thank Sheila Patek and everybody in the Patek Lab, John Christie and Maya DeVries, and a couple different groups from both Duke and UMass Amherst, as well as funding from the NSF and the Smithsonian Tropical Research Institute. And I'd be happy to take questions. Thank you.